This video is looking at gradients, and here we have a straight line, and if I take any 2 points on that line, let's take that point there and that point there, I can work out the gradient by looking at the difference in the y numbers and divide by the difference in the x numbers. So that is a difference of 4 in the y numbers, 2 in the x numbers, so I can say that the gradient is the difference in the y numbers divided by the difference in the x numbers. So that's 4 divided by 2, which is 2. So notice that I've used the notation dy by dx. This notation was invented by Leibniz, who was a great 17th century mathematician who, at about the same time as Newton, invented all the calculus we're going to be doing in this course. So gradients of straight lines are reasonably straightforward, but what we're going to be looking at in this video and for a lot of the A-level course is the gradient of curved lines. So let's start with the most straightforward curved line. That's on the next slide. So here we've got the graph of y equals x squared, well, a part of it anyway, and what we're going to try and find out is the gradient at the point where x equals 2. And to do this, I'm going to take 2 points. One of them is going to be at the actual point 2, 4. Then I'm going to take another point which is just going to be a little bit more than 2. Now, because of this diagram, I'm going to exaggerate it slightly, but the x coordinate of this point is just going to be a little bit more than 2. So let's label these A and B. The coordinates of A are obviously 2, 4. Why is it 4? Because this is the graph y equals x squared, remember. So to work out the y value, you square the x value. So this point here is 4, 2 squared is 4. As far as B is concerned, it's going to be just a little bit more than 2, 2.1, and so the y value is going to be 4.41. So the gradient of the line AB is going to be the difference in the y numbers, that's 4.41 minus 4, divided by the difference in the x numbers, that's 2.1 minus 2. So that's 0.41 divided by 0.1, which is 4.1. So now I'm going to exaggerate the graph and draw it really big, and imagine that this point was A and this point was B. And what we did on the previous slide was find out the gradient of the line that joins A to B. So that's meant to be a straight line. Now imagine that we didn't have the point B, but we had the point C there. We could find out the gradient of that straight line. Or suppose we had the point D there. We could find out the gradient of that straight line. So all these points, all these lines are, strictly speaking, chords, because they join 2 points. What we're trying to find out, though, is the gradient at the point A. So what we really want is the tangent at the point A. Now the tangent just touches the curve at point A, and I've tried this several times already on this video and replaced it because it's quite difficult to draw the tangent. That's not terribly good, but what I'm trying to draw is the straight line that just touches the curve at the point A. Now, as these points B, C, D, E, F and everything, as these points get closer and closer to A, then the gradient of those lines is going to get closer and closer to the gradient at the point A. And it's the gradient of the point A that we're trying to find. We want the gradient of this straight line. Now this bit is so important that if you're not quite sure, I suggest you replay the last minute of the video just to make sure you understand what's happening. These gradients as B, C, D, E, F, G, H, etc., as they get closer and closer to the point A, the gradient of these lines will get closer and closer to the gradient of the tangent. So what we're trying to find out is the gradient of any point on the graph y equals x squared. So I'm going to take any point here, and I'm going to say the x coordinate is x and the y coordinate is x squared. That's because the equation of the line is y equals x squared. And then I'm going to go just a little bit further up. Now, for the purposes of this diagram, it's a fair way, but I'm just going to say it's a small increment of x, just a little bit extra. It's x plus a little bit, and the notation is to use the delta letter. Delta, it's like a D with a curly bit at the end. And then the y coordinate obviously is x plus delta x squared. Why is that? Because y equals x squared. So if this is x plus a little bit, x plus delta x, then the y coordinate at this point is x plus a little bit squared, the x number squared. So what is the gradient of that line? Well, the gradient equals the difference in the y numbers, that's x plus delta x squared minus x squared, divided by the difference in the x numbers, that's x plus delta x minus x. Now if I multiply out x plus delta x squared, it's x squared plus 2x delta x plus delta x squared minus x squared, and then it's over x plus delta x minus x. Now I'm running out of room, so I've got a little bit of squashy work here. Obviously the x squared minus x squared is nothing, and x minus x is nothing. So I can write this as 2x delta x plus delta x squared divided by delta x. So I'm going to write that again on the next slide. And then delta x is a factor of the numerator, so it's 2x plus delta x all over delta x. Delta x divided by delta x is 1, so I'm left with 2x plus delta x. Now a bit more notation. The gradient, which as we said we use Leibniz's notation, the gradient of any point is the limit, and the word lim is often used for limit, so it's lim it, there we go, as delta x tends to 0 of 2x plus delta x. And if delta x tends to 0, then we get 2x. Now what's all this stuff about delta x tending to 0? What's this mean? Well, if you remember, if I do a quick sketch here, we had x squared there, and x plus delta x squared there. So what we were saying was that the x coordinate here was x, the x coordinate here was x plus a little bit, plus delta x, and what we want to do is to make that gap as small as possible. In other words, we want delta x to be small, 0 in fact, because the gradient of all those chords will approach the gradient of the tangent as delta x tends to 0. So if delta x tends to 0, then the then the gradient of these lines will become the tangent. So we're going to say delta x is 0, 2x plus delta x is just 2x. If delta x is 0, it's not the best delta I've ever drawn there, but there it is, that's meant to be a delta x. So what this is saying is that on the graph y equals x squared, the gradient is given by twice the x value. So dy by dx equals 2x. In other words, at the point 2, 4, the gradient is twice the x value. 2 times 2 is 4. That's what we had at the start of this video. Squash it in here. At the point 3, 9, the gradient dy by dx is twice the x value, 6. This is an incredibly powerful formula, incredibly powerful way to look at the gradient of a curved line. And one of the beautiful parts of mathematics is that what was a particularly complex situation now becomes very straightforward and easy. To find the gradient of a curved line, of the curved line y equals x squared, then all we need to do is to double the x coordinate. It's different for x cubed and x fourth and x fifth and sine x and cos x, and that's what a lot of the rest of the course is about. But for y equals x squared, then the gradient is given by twice the x value.